I'm Felipe Hoffa.
And I'm Ray.
Yes, we're going to talk about Google Dataflow, the new open model for batch and stream processing. We are developers advocates
For the Google Cloud Platform.
Yes, and we're super happy to be doing this talk together today. It's my first time speaking with Ray.
And this is my first time speaking with Felipe as well.
Yes, so that's pretty cool.
Wish us luck.
Yes. Just to know, show of hands, who's working with big data? Oh, a lot of hands. Streaming data. Cool.
Right. Awesome.
Dataflow. Oh, you know Dataflow. Excellent. A lot of hands. Apache Beam. A couple now. So that's where we end our talk. So this is Ray. You can follow him on Twitter at Saturnism.
And that's Felipe Hoffa. You can follow him at his name, actually, at Felipe Hoffa. That's kind of nice.
Yeah, so let's get this started. Let's look a little bit at streaming data.
Yeah. So Felipe actually found this application. It's actually written by one of the Googlers. And what this application does is that it's monitoring live Wikipedia editor edits, right? Like the changelogs. They publish it in a streaming fashion into IRC channel. And it's trying to aggregate these streaming data and trying to extract insight into the data. So what this one particularly does is to try to figure out if there's a heuristic that it can take to figure out breaking news. Why? Because when there's a breaking news of some sort, usually people will go to Wikipedia and they will be editing these articles. And so the heuristic here is very straightforward. It's looking for things such as that has a single article be edited more than 5 times. And in between the edits, if it's being edited frequently, between 1 minute. And also if there's like more than 3 different editors editing the same article concurrently. So it's trying to get insight from streaming data. And we're going to look at how to actually accomplish this by using Dataflow.
Exactly. So we want to re-implement this with Dataflow as it's our new paradigm. But let's start some years ago and let's look how we ended up with Dataflow at Google. First, if anyone knows this paper, the MapReduce paper from 2004, that's what started today's big data world. We could call it a very important step. And the basics of MapReduce are, instead of using one big giant computer to process everything, is being able to separate our job between many computers and then do this job in parallel. Now, if each of these elements that we have transformed, we give them a key, we are able to shuffle group them and then produce results in the next step. And thus, instead of having a big computer, just using a lot of cheaper machines. And that was the MapReduce paper that we started using at Google that got implemented outside Google as Hadoop. But many years later, we released the Flume Java paper, because working with MapReducers, as they are, it's pretty complex when you want to chain them together, when you want to get the results from one to the other, and then optimize those steps. So Flume Java took care of that. How do we just write the code that we want, like with a high-level API, with simple data processing abstractions? We just code our goal, what we want, and then the system takes care of chaining all of these steps, optimizing them, etc. We have some code here.
Yeah, so imagine that if you have a bunch of, say, IoT sensors all over the world, and they are keyed by the location, which could be a string in this case, and they're sending you temperature data that's in double. So typically what you may be doing in the past is that you could be collecting this data and processing it in batch fashion, and then you write a MapReduce job, right? And you have to decompose them. You have to think about how to write that MapReduce job. With Flume Java, in this case, there are a few things that's very important. The data that you want to process is called the P collection. It's basically a collection of data that you want to process. And it can actually be a batched data you read from a file, or in some cases, you can actually do it with streaming data, which we'll talk about in more detail later. Now, once you receive the data set, you can then apply some kind of function to each of the element. If you want to apply the functions to each of the element in parallel, then all you have to do is to add pardo, which means parallel do. And then you can apply this parse function, which will then parse the data for you. And then you can group them together afterwards. You can do a group by key, or in this case, we're basically grouping, and then we're calculating the mean. And as you can see here, it's a pretty straightforward top-down in a linear fashion to define your data processing pipeline. You don't have to decompose them into individual MapReduces. It will be done for you behind the scenes.
Exactly. So we have big collections for big collections of elements, the ability to do stuff to each of those elements, and the ability to group them by key, and then get our results somewhere. And we started using this at Google, in fact, from 2011. This is what all the Nooglers started learning as part of their Noogler class, how to process data, lots of data with Flume Java. And this has some limitations. When you're processing data with batch, you need to set up some boundaries, for example, day boundaries, Tuesday, Wednesday, Thursday, that also brings problems, for example, latency. Do I have to wait all day long to get my results? Yeah, and even then some, because we don't get data in real time. Sometimes data is delayed. Also, sessions are a problem. Not all the information from one day ends up at the end of the day, but there are sessions that go over, and dividing data by day will break sessions without our ability to process them. And this, as it is, this slide shows, data is unlimited, data never stops coming, so we needed a different way to process streaming data. We are not dealing with batch anymore. And that's where the next paper comes, from 2013, Millwheel, how we started processing streaming data at Google. It's a similar framework for building low-latency data processing applications with a direct acyclic graph of computations to be performed, where the system manages the state and persistent flow of elements. So we were able to write these pipelines that process streaming data that were not always correct, but at least we got results in real time. For example, when we're processing streaming data, it's super simple to grab each element that is arriving and output its transformation. But grouping them, getting windows, is a little more complex. A typical way of dealing with streaming data is dividing it by hour, by minute, etc. But this is a challenge. Data doesn't come in order all the time. So for example, if I'm receiving an element now, it doesn't always belong to the window we're processing now, but maybe it was emitted, the real time of that event was 2 hours before. So I need to keep different windows open. I need to keep process each element in the window that it really belongs. That is not really the time when it arrives. Same thing with sessions. For each element that arrives, we need to decide to which session does it belong. And that's where, from Millwheel comes this critical concept, the watermark. What are we seeing in this chart is the two axes. One is event time, when things really happen, versus processing time, when we are getting these elements. And the ideal would be to get process each element as it arrives, but that's not possible. We always have a skew.
Yeah. So the skew is actually the fact that when your event has occurred, it has to actually travel through the internet somewhere, and it has to be getting to a message queue of some sort, and then some workers is going to have some kind of delay before it gets processed, right? So the skew is really the delay between when the event happened and versus when it was supposed to be actually being processed. And also, more importantly, as the data is arriving in a streaming fashion, you actually don't know when the data is going to arrive, and sometimes you're going to get this delayed data as well. And so you actually have to figure out, the system has to kind of figure out or guess in a way that when is it the time that we're not getting any new data for this specific event window, for example. And that is actually the watermark. That's when we feel like, when we think that there's no more data that should be arriving, and then we can go ahead and say this session is over or this window is over.
Exactly. So it's impossible to know the perfect watermark. We don't know if there will be more late data arriving. But the watermark is when we believe that there will be no more data arriving. This is an important decision when processing streaming data. And the two possible problems are if the watermark is too slow, our results will be delayed. We will be waiting for data that's never coming. But if it's too fast, there will be late data that we will need to process somehow. And this is the state of the art until recently, the Lambda architecture. As the streaming processing is fast, we only got approximate results, not perfect results, and having exact results is important, so we were redoing everything in batch and then connecting the dots between each other. But this is not ideal. We don't want to have two parallel systems processing data. The ideal would be to have everything in one. Instead of deciding between having complete results, or the latency of them, or the cost of these results, we try to compile both streaming and batch in one common model, and that is Dataflow.
So in Dataflow, before we jump into each of these in detail, there are actually four really, really important concepts: the what, the where, the when, and the how. And we're going to go into these in detail in a second. The what is basically what result do you want to have. That also includes the steps to calculate the result. But remember the items that's going to arrive, it has some kind of event that's occurred, and it has an event time. Now, where does that item actually belong in terms of event time? You actually have to figure out, and we're going to be talking a little bit about how you can window them into different buckets. And then, when are they actually going to be processed? Whether that if something comes in late, do I need to process the late data or not? If something comes in early, do I have to trigger the flow to continue early before all the items that's arrived? And then sometimes you have to refine them. So for example, if it does occur early or late, you need to be able to say, okay, do I need to emit the aggregated result from the late data, or do I just don't care and just emit the late data as well? So we're going to go into each one of them in detail.
Yeah, so the critical thing here is being able to separate all of these concerns instead of having all of them mixed in the same code. If anyone has been working with Spark, answering these four questions, coding for them, means you have to mix all your code up instead of having them very clearly expressed, as we're going to show you now. So the what is what we want, the results we want to produce with the data we have. We have some basic elements in Dataflow. The part do we saw before, do something to each element, map each element, aggregating them, either by group by key or combining them, and also the ability to do composite operations, like let's combine the part do with the group by key, etc. We have some code here.
Yeah, so this code is very similar to what you saw previously, like Flume Java, because Dataflow is an extension of that. And so, as you can see here, was also dealing with P collections, and you are able to read the data from some kind of I/O. And this thing can be different, right? For example, if you are to read from a file, this can be text I/O. If you are to read from a PubSub messaging system, then you can change this to PubSub I/O. It can be something else as well. And then you send this through. If you want to process the data in parallel, like I mentioned before, you do a parallel do. And then most importantly, in the end, maybe you want to aggregate everything together. Previously, we had an example of calculating mean. And this time, we're going to be calculating the sum of integers per key. And this is important for some of the graphs that we're going to be showing next.
Exactly. So we want to add integers with this code, simple code. And let's see how this would work in real time as we are processing numbers that are incoming. That line is the ideal line. There cannot be any element that comes before. We cannot get elements in processing time before they've been produced in event time. For example, the 3 is pretty close to that ideal line. That 3 was created at 1206, and we got it into our system at 1207, approximately. And then the 9 was produced even earlier, about at 1201, but we didn't see it in our system until 1208. That's an example of data arriving late. Now, the code that Ray just showed us would process each element in a batch way, where we wait until we have every element, and at the end of time, we output the result, 51. That is the sum. And we could do something similar if we wanted to code this for the Wikipedia example.
Yeah, okay. Oh yeah, Ray codes, how convenient. All right, so here we have example code, which actually works. This is actually what's being deployed, but it's not complete at this moment. So remember, the first concept is what? What are we computing here? Well, what we want to do is to be able to retrieve the streaming data from Wikipedia, and then what we want to do is a sequence of steps to calculate the result. And the final result that we want is obviously the breaking news that could be happening. So the series of steps it takes to get to that result, for example, can be documented in this way in the code. First of all, I need to map each of these incoming strings, and I need to map it into actual POJO. So I can, because I'm statically typed person, so I love to convert everything into a POJO. And in Java streaming, for example, you can have a map operation, and in Dataflow you can have something pretty similar, but you do have to say something like a map element, right? That's the operation I want to use, and then via a mapping function. And this mapping function is pretty simple and straightforward. If I scroll down, if I see the mapping function that's right here, it really just takes in a string and it returns the POJO. I'm using JSON as well, so it's a pretty straightforward conversion. And then the next step, of course, is I need to extract the key from this POJO. And this POJO actually has, let me see here, quite a few fields. And the key that I'm going to take from the changelog is actually the title, because I want to know how many times this particular article has been edited and how many people were editing it within the same time frame. And so the key I need to extract here is the title, so I can just extract that. So let me go back to the pipeline. Yeah, right here. So I can say with key of key by title. And again, this is another function that I created for convenience. And inside of it, it's basically just returning the title from the object. And then finally, I'm going to group by key. All I have to do is the group by operation. And then in the end, once I group everything, I'll have the key with a list of items I need to process together for that key. Then I have an aggregating function here, which I'm going to count in parallel, because here I'm using a parallel do. I'm going to count how many times the logs has appeared, and also how many editors, unique editors are there as well, and a few other metrics. So it's pretty straightforward.
Yep, pretty simple way to code step by step what we want to do with these elements. If we were reading these rows from a file, we would get the results whenever the file is done. But in this case, when are we getting the results?
I thought we would just be getting this continuously. No?
Continuously when?
Well, yeah, you're right, because at the end of the file, you have EO file, and then you just emit the result, but the data is continuously arriving, so I guess I'll never get a result in this case.
Exactly. So as we are grouping things here, we don't know when the groups will be over, when we'll be done with them. So that brings us to the next slide. Excellent. So what we can do here is window. Get all of these groups by fixed windows in time, sliding windows if we want to get the same element in different windows starting at incremental time, or even in sessions. And that's the where that we will be showing the slides as blue code. For example, here on our sum of integers, we are introducing a window of 2 minutes. And this shows where we want to have our elements group, the where in event time. So as we were getting without the window, we were getting the whole sum. Now we're getting the sum per window of 2 minutes. And this where only gets us the results at the end of time, when everything is processed. In the case of Wikipedia, if we wanted to do windows, we would.
Yeah. So we can definitely apply windows here, right? Because right now I'm trying to group by title, but I need to know like the period where I need to group them together by. And we can also do a fixed window, but I don't think that's going to get us the right result because the data is arriving continuously, and I kind of want to have something different. I want to have like a sliding window instead. So I'm going to have a window, for example, of 5 minutes, because I want to aggregate data in between that 5-minute time frame per article, right? So that it's grouped by key. By the title. But then I also wanted to slide every 10 seconds or so, right? So every 10 seconds, I should be able to slide the window to the future a little bit so that I can get the latest 5 minutes of time. So to do that in Dataflow, it's pretty simple. I can just do apply. Everything in Dataflow, in the pipeline, you kind of do apply. You apply some kind of function. And then I can do a window function. So I can do window into. And then I can just do a sliding window of a duration. By the way, this is Jola time. I can say this window has a duration of 5 minutes. And then I want to slide every certain moment, certain duration. So I can say I want to slide every 10 seconds or so. Okay. And that's pretty simple. Now I'm actually, I have the what we're computing, and then we're grouping them, we're sending them to the where, which is the correct event time window. And so we can group them together.
Exactly.
Yeah.
But we're not getting the results.
Still not? What?
We are still not getting the results because we are not asking when do we want them. Slides. Yes, so as we were looking here, the beauty of asking where is that independently of when we receive the data, it's all getting into the correct window. But this is not telling us when we're getting the results. We're getting the results at the end of time that never comes when we're doing stream processing. Here comes back the watermark we were looking at before. If we have a watermark, if we know when we are done with the window, we can trigger to get results either early, before the watermark is done, at the watermark, and after the watermark. We have some code here. For example, this trigger is sometimes the default behavior that we will get results whenever we think we are done with the window. Now we have different results here. This is the ideal watermark. This is the perfect watermark that waits until the 9 comes. But in real life, we don't know if the 9 is coming or not. So the system will guess, with its heuristics, that maybe no more data is coming here, I will emit a 5. And then the next window gets the correct results, the next window gets the 3. And the 9 arrives then, and basically it arrives too late. We're not getting the 9 into the correct window because the watermark is done. And we don't know we didn't specify how to work with this late element. But we could add those triggers too. Hey, I want early results. I don't want to wait until the window is done. Give me a result every 1 minute. And if there's late data coming, emit those results too. And thus, if we will look at the right side, here we get the 5 on time, and then the 14 as a late result. Same with the other windows. We get early results now. So even before finishing, we know somehow what's happening there. And then we get the correct result when the time of the watermark comes. And I think we should code it.
Yeah, how do we apply this? I mean, what would be a good use case here for this particular example then? Mm-hmm. So for example, we're taking the streaming changelog data from Wikipedia via IRC, and maybe IRC is being slow, or that the event just didn't arrive in time, and sometimes we could be getting late data, but I still want to process it because that data belongs to the right sliding window that I created, and that actually could indicate that there's a breaking news, but it just arrived a little bit late because of the infrastructure, for example. So I want to be able to deal with that. So for that, what I can do is to add the triggering, like what Felipe showed in the example here, except I'm going to do this live. And I can trigger this after the watermark, past the end of the window. As you can see, this is very fluid. It's almost like constructing an English sentence here. And then I can say with the late firing, and I can say with the late firing processing time, that past the first element in pan. And that's it. That's pretty much it. And because of the typing, I have to do a strong typing here, do a string. Yeah, and all the arrows goes away. All right. And then we have another problem. So now I want to wait and be able to process late data, right? But I also can say with a lot of lateness. and I can give it a duration as well. So I want to wait up until, say, 1 minute of late data. So I can do that. But we have another problem. The sliding window is 5 minutes long, and it's going to slide every 10 seconds. But within the first 5 minutes, we're going to wait for the first 5 minutes to complete. But during that time, I still want to get some results early. Why? Because maybe there are breaking news that's happening already within the 5 minutes. Maybe by the second minute, I already have the breaking news. So I don't want to wait for the whole time. So what I can do then is by adding an early firing in here. So I can say with early firing. And what I want to fire, when I want to fire early, is that before the 5 minutes is up, maybe I already have 5 edits together already, and that's a pretty good indication maybe I have something in hand. So I want to trigger this event, trigger the processing of this pipeline. So what I can do is I can say after pan, and element count at least, say 5. Okay? And now we have a complete set of the window, not just the window, the where, but also the when. So I can deal with the late data, and also I can fire early as soon as I have 5 elements in my collection for that group. Yeah, it's pretty
cool.
Nice. Yeah.
Now we're getting results on time, before time, and even processing late elements.
Right.
We have a question.
So if you say that you get 6 results in the correct time frame, you process them, and a couple of time frames later you get something which was for that correct time frame.
Yeah.
I don't know if I fully understand. Does it go back and reprocess the entire...
I love that question. So the question is, what happens when we get a late element? Do we go and reprocess everything that we had already, or do we process only the late element? And that question is the how.
Yeah, that's great timing, by the way. There's no coordination here, but let's get to it.
Yes, how do refinements relate? That's the exact question I got there. And when we get multiple results per window, how do we process them? Do we calculate again the entire sum? Do we only process the values that have come since the last result? Do we retract the results we gave earlier? And in this case, with an instruction like this, accumulating failed panes, we just reprocess the whole window. Every element that we already had is considered in the new result. So yes, we get 5, and then we get with the late data 14. We could have a different strategy. We could have only say 5 on time, and then hey, the next result is 9, and then downstream the next element in our chain processes them accordingly, and that all depends on how do you want to get your results. And we're able to express it with the Dataflow programming model. Thank you for that question. Do you know where we're going now?
No, but I have another question.
Okay.
If you have a stream which is, for example, on this Wikipedia example, you said you're getting the hits via IRC or whatnot.
Yep.
Say that service is just generally running slow for a couple hours. They're trying to fix it. So every single thing you're getting is half on time and half late. Does that mean you're just going to start overpowering your system if you're reprocessing every window more than once or twice?
So what happens when we get too many late elements, and what happens to our system? So the system the runner of our code has to decide what's the perfect or best watermark for the process. That algorithm depends on what the runner decides, and there is a full talk of how we are working with this and how we decide what the perfect or the ideal watermark is given the conditions, how late the elements are arriving. But that's a full another talk. But yeah, it's an excellent question. Getting the correct watermark that processes elements on time is the challenge here. But yes.
Let me just make sure that this code is going to work. So I'm going to also accumulate the fire pan so that when there's late data from Wikipedia, in this case, arrives, I want to make sure that it's grouped with the previous result within the same time window so that it can trigger potentially breaking news as well. Okay. But I think that there are certain cases where if you're accumulating forever, then that's not good, isn't it? Yeah. All right.
Well, yes. So we saw here how the same code, the yellow code, we were able to get big fixed windows, how we were able to process streaming data in real time, how to get late data and early data, and how to get either accumulations, and we didn't see the incremental results, but they would all work with the same code and just treating each concern separately. And it's time to see if this is working.
Yeah, so this one's working, but that's not my application. So, so let me see here. Okay, so before I show you that, let me show you how you can actually deploy this pipeline. There we go. And zoom in. There we go. Okay, cool. So, so this is Java application. And this command line is a little long, but that's only for my convenience. You can definitely simplify this if you want to. But the key here is that the first thing that you want to do is to compile this application. I'm just using Maven here. And then all you have to do is to execute it. Now, as soon as you execute it, because I created a self-contained jar file, as soon as you execute it, you can give it a few parameters if you want it to be more configurable, or you can add it into a property file. You can configure it in the code if you want to. And what it's going to do is it's actually going to upload itself. It's going to upload the jar file into a location somewhere that is you're going to execute it. Now, because we're running this in Google Dataflow, which is a managed service that's on the Google Cloud Platform, what this is going to do is it's going to upload the jar file into a storage bucket in cloud storage. Basically, that's where we can store a lot of data. And then once the jar file gets there, we are going to manage the spinning up of the machines. When we're going to deploy it, and it's going to run. And that's really what it does. Should we deploy this?
Let's deploy it.
Yeah. You are very adventurous. But this is going to take a little time to deploy. As it is deploying, it is going to, I added this update is equal to true flag. What that means is that, where is it? Here. Update is equal to true. So what that means is that it's going to try to replace the pipeline that's already running. And the pipeline is actually here. This is the pipeline that's currently running right at this very moment. If I have Wi-Fi. There we go. Yeah, that's always the problem, isn't it? All right, here we go. So you can see that this is in the running the runtime environment where they actually parsed my Dataflow code in a way like this code, what we call deferred execution. So we can actually go back and reconstruct this tree, and then we can display this on the GUI as well. You can see that the first step is going to take is reading the article, and then we're going to window it, and then we're going to do all of these processing. You can name each step as well, so you can see the pipeline very, very clearly. And if you go into it, you can actually see how long it's been running, and also how many elements is added, and also how many items is processed per second approximately. So this pipeline is running, and not only is it trying to identify breaking news, we're also sending data directly into BigQuery, so your pipeline can have multiple syncs, right? So we're processing, trying to figure out the breaking news, sending it to BigQuery, and then also sending it to a place where we can see streaming data. And there's the streaming data right here. And I think it's not streaming anymore. No, it stopped streaming. Why? Because the new job is being deployed and it's just coming online at this very moment. So it stopped the previous job and it's trying to bring up the new job. But we can see what's actually being streamed here. If it was streaming, you're going to see all the latest article here, and then the different articles that we're grouping by. We're trying to find the top 10 candidates we're going to display at the bottom in gray. And then for the breaking news that we identified throughout time is actually going to be listed down here. So it's going to take maybe a few minutes for it to deploy because we're also provisioning the VMs in the back. And we can probably talk about something else and come back to this.
Yeah.
Assuming my code works. Yeah.
Exactly. Well, the cool thing here is that Ray was just coding, and then when he deploys to the Google Cloud Dataflow running environment, Google takes care of setting up machines, auto-scaling up or down depending on how many elements, how expensive the job is, less computers, more computers. And then we are able to visualize everything in real time. We're doing that with Firebase, and we're able to get these elements. So let's look at the other elements in this pipeline. How about that?
Yeah. So let's see here. One of the things that I didn't get to talk about was like, oh, how did you actually send the data to BigQuery, for example? Now, here is where we're reading the data from. This is the streaming data from PubSub. Now, PubSub is our managed messaging service. So rather than running your own messaging service, you can run it on Google Cloud Platform as well. But this is actually where we're just pulling for the data continuously. And once I have this stream, I can say stream and send the data to BigQuery. Done. That's pretty simple. But no, I simplified this a little bit as well. So if I go into this function, let me do a go-to declaration. There we go. You can see that you can actually group, you can aggregate or combine different operations, and then you can create new operations if you want to in this case. So I combined a few operations together because I want some convenience method for me to send to BigQuery. So here I can just specify the table name. I can get it from the options. And then I can say where in BigQuery do I send this to. Essentially, this is saying which table do I send this data to. And if the table doesn't exist, I can create it if I need to. So all of these things are pretty configurable as well. The other thing I didn't really talk about is how do we actually group the keys together and also getting the top 10 results, right? So here we have group by title. We're going to do an aggregation. And then from there, I want to see the top 10 result. The top 10 result is based on some kind of comparator that you're going to create. So all I have to do is to create another step here. So after I got all the results for cluster them together into different articles, and then I can say, let me find the top 10. And I can use this top off operation, the top 10 off, and the comparator. And if you go into the comparator, this is a pretty standard Java comparator as well. If I go into declaration, you can see it's just implementing the compare function, and we're just comparing the number of changes. So supposedly what we're going to get for the top 10 is the top 10 articles where they have the most number of changes. Now, if I want to change this to having the most number of editors, all I have to do is to change the comparator, or I can actually use a different one as well. So let's see if this pipeline is running. Now, there we go. So it is running right now. Oh, thank goodness. The code works. If I go back, let me see here. Let me do a refresh. And there we go. Now you can see the streaming data coming in. You can see the top data that's coming in right now. Right? That's the top 10. And you can see that some of them, I should probably zoom in. You can see some of them has more than 5 edits. And this one in particular has edits between 60 seconds. So it's getting pretty close. If this item gets, say, 3 concurrent editor, then there's something going down with Shaolin Showdown versus whatever.
Nice pronunciation.
Yeah.
Cool.
Yeah.
Cool.
But there's no breaking news right now. Yeah.
I've seen breaking news before.
Yeah. Oh, have you?
Yes.
I don't remember that conversation.
Maybe we have that on a slide.
Maybe it's not a conversation I had. So should we go see that right now?
Or should we? Okay, if you want to.
Yeah, why not? And we'll come back to the other stuff. So I wonder what conversation you're talking about here. Do you want to see the breaking news first or the conversation?
The conversation.
The conversation.
So why we
I don't want to
this?
see the conversation. I don't know who this person is.
We had a conversation like, Peter Schaffer was in the news. Oh, he died. It worked.
Now, I don't know who said this. I don't know what that profile picture is. I have no idea.
Oh, yes.
Yeah.
I replied, whoa, take a screenshot. And basically, yes, I'm sorry for Peter Schaffer, but we really saw this working, how more than 3 concurrent editors, more than 5 changes, less than 16 seconds between edits, boom. We were able to detect that things that were going on the Wikipedia stream were really news. And
this person was obviously very excited, so that he messaged Felipe to tell him that this thing actually works.
It's working. Yes. So we have 12 minutes left. Let's review some of the other elements.
Yeah. So how do we actually get the data in here? I think that's probably on the first question. And I don't know if anyone used IRC. Anyone used IRC before? Yeah, I used IRC a long time ago. I had a funny story to tell, but I probably shouldn't say it here. Let's see here. So Wikipedia publishes the IRC. Publishes the changelog into the IRC. So I have it here. I'll show you just very briefly what that looks like. So if I join, let me zoom in. Nice. Wow, magical. All right. So if I zoom in here, I can say join in.wikipedia. And you can actually see the data that's coming in, and it's coming in quite fast. And we're not just monitoring one language, right? We're actually monitoring like, I don't know, almost 100 languages or something like that. I don't remember. But we're monitoring many, many languages. And this thing can accumulate very fast. And that is the streaming data that we have. Now, so how do we actually get it into Dataflow so that it can be processed? Well, first of all, we wrote a Node.js application. Sorry, Mario. It's a Node.js application that will then take... If you don't know Mario, you should talk to him later. And what this application does is that it's listening to the IRC channels, and then it's just pulling the data. And then as soon as you receive a message, it's pushing it to PubSub via the API that we provided. In this case, we have client libraries you can use. And then it's going to push it into PubSub. Like I said, that's our managed messaging system. Yeah, there we go. And it's pretty nice. It's pretty nice so that you don't have to manage your own queue. I mean, anyone who set up a GMS queue before cluster environment and such, you know how painful that could be. And it takes a lot of time to manage it. But this is actually globally distributed with the minimal latency and a bunch of good stuff.
With zero pain. It just works.
It was zero pain, yeah. It
Yes.
just works. Yeah. So we're pushing data into PubSub, and then Dataflow is reading it as well. So the line here that you got to remember is that, remember you can read the data from many different sources, and you can read it from a batch fashion from a text file. In this case, from PubSub, I just have to use pubsub.read, and then give it the name of the topic that I need to subscribe to, which is pretty straightforward.
Yes.
Yeah.
And Firebase.
And then how do we actually do the real-time streaming? As you can see, this is streaming live, and this is streaming live fairly quickly. Now, typically, what developers do today is by using WebSocket, right? In fact, that's what this other application does, the other simple application. They use WebSocket. But you also have to manage the connection. You have to deal with WebSocket and sometimes continuation and a bunch of other things. So rather than doing that, to stream live data, to send this data to my browser, I'm actually using Firebase. How many people actually heard about Firebase here before? Quite a few. Awesome. Yeah, Firebase is one of the best thing I've ever seen in my life for a long time. And what it is a real-time database. That's the important part here. It's a NoSQL database, fully managed and hosted for you, and it gets you the data in real time. What that means is, right now, I'm pushing the aggregated data into Firebase, and whenever I push something into Firebase, all the subscribers, all the people that's watching the Firebase with the right privilege, of course, gets this data in real time. Okay, so whenever I push from Dataflow the latest news, I'm seeing it into Firebase, and I'm getting these messages and events in real time. And you can have as many subscribers as you want to see this file, to see the database as well. So whenever something gets updated, you get to see this in real time.
Nice. And speaking, and this is how we write to Firebase.
Yep.
And this is, well, we already saw this, our conversation. And speaking of favorite things on the world, my favorite thing is BigQuery. Anyone knows BigQuery? Yes, we have some hands. If you want to analyze a lot of data with SQL without any servers, just put your data on BigQuery and it will analyze as many rows as you have, billions of rows, in very few seconds. Just to demo it.
Yeah. So let me set Felipe up for this.
Where is my
Because
table?
he doesn't know how to use my computer. He doesn't.
It's a complicated computer.
Yeah, I know. Okay, so do you want me to refresh this? Yeah, I'll refresh it just in case.
Okay, so this is one of the web UI for BigQuery. You can connect it via REST API to anything else. But the web UI is pretty cool when you want to get fast results. So I've been storing all of these elements for a long while. Here is my table. I was using WebObjects. Sorry, the streaming API, so it stopped working at some time. But in this table, I have all of my objects stored. Basically, I have 50 gigabytes of all of the changes produced by Wikipedia, 100 million rows.
100 million rows.
And I stopped getting them on June 1st, but still. All of these elements are stored here in only one column. Basically, I'm storing a full JSON object that I'm able to parse in real time. In fact, here I have a view that just looks at that table and JSON extracts each of the columns. So, for example, if I want to get for each day the pages that were not edited by a bot, and I want to group it by title, by day, with more than 100 changes, more than 20 editors, and get the top for each day, a query like this should run pretty fast. Let's see how much it takes.
So there's
Today?
100 million rows in there?
Yeah.
Yeah, 50 gigabytes of data.
It's a little slow, but I will blame the Wi-Fi.
It's always the Wi-Fi.
Yeah, of course, it's the Wi-Fi. But the thing is, in very few seconds, I'm able to find the top one, and using SQL, I'm able to look at my the results I get, and I'm able to refine my algorithm to find what's the sweet spot of what should I be asking for. Sigmund Freud changed a lot on May 6th. Maybe it was the page of the day, but there was also the equator, earthquake, etc., etc., etc. Kobe Bryant on April. And thus we can go back and see all of the elements. I could not do this presentation without talking about BigQuery. Yes?
Does it support temp tables? And if so, where's that stored?
Does BigQuery support temp tables? Temporal tables? Yeah, so whenever you create a table on BigQuery, you can say if you want that table forever, or if that table will last only for 1 day, or 10 days, etc.
Yeah.
Also, every time you get results, that's a temp table by itself, unless you name it and want it as a permanent table.
We have two breaking news here, but I'm not sure what they are.
Yes.
Yeah. I don't. So sometimes the heuristic, because I'm not taking account of bots, for example. So sometimes somebody edits something and then the bot reverses the edit very, very quickly. And now all of a sudden you have very fast, frequently edited article. If the person does it 3-4 times, then it will actually show up here as well. But I haven't been able to take account for that at this moment.
Yes. 5 minutes left.
Yeah,
Let's talk
all right.
about what's
coming.
what's the present and the future.
Yeah. Oh wait.
So,
that's
kudos to Spotify. If you want to see real use case of the same technology, pops up Dataflow BigQuery. You can read the blog post from Spotify where they took all of this technology and adopted it, replacing their previous stack. And so that is a pretty cool and much bigger use case. But they didn't code it live here, so it counts for something. So the future, how do we go from Dataflow to Apache Beam? As we saw today, Dataflow has two parts, the model and the SDK that we open sourced, and Google Dataflow, the runner. The thing is, a lot of other frameworks wanted to adopt this model and this SDK, but it being controlled by Google was a limitation. So now, since January, it's an Apache project, Apache Beam. So it's now part of the community, and it's our as the community, unified model for batch and stream processing, supporting multiple runtimes, where Google Cloud Dataflow is one of those runtimes. In this model, you get the what, where, when, and how that we saw today. You get the SDK for writing Beam pipelines. Today we saw the Java one, that's the first one. There's a Python one almost ready. There's a Scala one being written by Spotify. And there are multiple runners. Data Artisans is writing the runner for Flink. Cloudera, the runner for Spark. Google has the fully managed service. And of course, there's also a local in-process runner for testing. This is basically the technical vision. How we have end users that use the model, SDK writers that write this the SDK in multiple languages, and runner writers that take care of running your pipelines wherever you prefer them. So yes.
Yeah. So one of the good reasons that we're here is that Apache Beam is just getting started, right? And we want your participation as well, whether usage or just trying it out, or actually being able to contribute as well to collaborate with the community. It's very, very fast growing, and we are hoping that the Beam will become like the model that you use in order to create your data processing pipeline, regardless of whether it's batch or streaming
or which runner you want.
And be able to run wherever you want.
Too
And
many-
yeah, so the project was in incubator in February, and in early 2016, which I think is right now, it's a little chaotic in a way, but that's only because we just open sourced and we have a lot of contributions, and we're looking to refactor the code, right? So we're making a lot of changes to fit the community needs. So it's in flux, right? It's being changed right now.
June 1st, we had the same release, the first release.
Yeah. Yeah, no, nice. And that was the mid 2016, and that's where API is being hopefully stabilized, and we should be able to convert our code and use the Apache Beam SDK instead.
So for our last minute, 1 minute left, MapReduce was the original paper that was followed by a lot of other papers that were followed by a lot of open source products, but we want to change this way of doing things now. With Google Cloud Dataflow, you got an open source project to a paper, an open source project, a runner, and now Apache Beam that is unifying both worlds. Some links for Apache Beam. That's me on Twitter. That's Saturnism on Twitter. Feedback is always welcome. Hopefully you enjoyed this talk, and thank you very much for waking up.
Thank you.
And I have a better answer for your question, but I think time is up. So we'll be here if we can help you in any way. Thank you.